Hello, everyone and audience. Today, I'm going to talk about the topic of an application of reinforcement learning to credit scoring based on the Logistic framework. This is done by me, Kantapong, and my advisor, Associate Professor Dr. Seksan Kiatsupaibul. Okay, let's start with the motivation. Well, the automated credit scoring is a universal tool for the online platform. Let's say, if we talk about the traditional approach, it considers model construction separately from underwriting process. This is called the greedy algorithm. But there are more efficient learning algorithms available in the RL toolbox, for example, Thompson sampling. So this work is based on the Logistic Bandit framework, which is the framework that is built on the logistic regression, and this is considered the industry standard for the banks today. And this study will apply reinforcement learning to the credit scoring, where different algorithms will be evaluated under the logistic Bandit framework. And and the different algorithms will be explained in the next slides. So let's start with the environment. Well, this logistic bandit framework environment consists of an action set, which is among n available borrowers, select k borrowers to provide the loans. And the observation set is that for each k selected borrowers, does the borrower default or not? And we signify 0 and 1. 1 means non-default so that the agent is better off, and 0 is default, so the agent is worse off. And then the observation probabilities is the ground truth non-default probabilities represented by this formula here. So let's think of three components as the basic building blocks for RL. Because with these three basic building blocks, we will have the interaction. That is the interaction between the agent and the environment. So we have the question, with these three basic building blocks, how do RL reinforcement learning agents interact with the environment? So the environment is characterized by beta, and beta, it is the ground truth beta that represent the formula here. And agent doesn't know this, okay? So the agent does not observe this one, but has to estimate the beta hat from past observations to infer non-default probabilities of all borrowers. So after the agent estimate beta hat with the model and select the borrowers. For example, for 5 borrowers, if the agent selects 2 borrowers, so the outcome for the 2 borrowers will be either 1 or 0. So the first borrower is 1 because he does not default. And the third borrower is 0 because he defaults. And for the other, we don't know because the agent doesn't provide the loans. Regarding the algorithm specifies how to select an action. So we start with the basic thing first, that is the greedy algorithm. Basically, the greedy algorithm will fully exploit the received information without exploration. And second one is the epsilon greedy algorithm, which is the greedy algorithm but with a small chance to explore by sampling uniformly from all possible actions. And the third one is the Thompson sampling algorithm, which is the algorithm that we seen in the first few slides, which I claim that it should be more efficient because it performs exploration by choosing an action that agent has limited information about with high probability. So the technical note here means that the formula of Thompson sampling algorithm, when we applied it to the logistic bandit, there are a lot of technical details that we have to deal with, but I just put here for the reference. How about the evaluation? Well, there are two performance measures that we take into account. First, the rewards. So if the borrower does not default, the agent gets 20% interest rate. If the borrower defaults, the agent will lose the whole principal. What does this mean? This means that the agent will get 20% interest rate. And this interest rate is considered making sense in, let's say, for example, the microfinance loans. And the second performance measure is a regret. Regret is the difference between the maximum expected reward over all possible actions. That is the best case if we select it correctly, and the expected reward of the taken action. So this measure requires the use of ground truth probability of non-default because regardless of whether the borrower defaults or not, if we choose the correct one, the regret will be zero. So this motivates the use of a simulation study. And we shall show this using the results in, let's say, in the basic scenario. So we start with the simple setting first. In the simple setting, the agent selects a single borrower among all available borrowers, and we will face the same set of borrowers in every time step. That is the simple one, study in traditional reinforcement learning, and we set the number of time steps to be 250, which is quite long enough. And the borrower features is described using two-dimensional vector. And with all this, the result confirms the common belief in the traditional reinforcement learning that first, the epsilon greedy outperforms greedy because of an exploration. And second, Thompson sampling algorithm outperforms the epsilon greedy because of an efficient exploration. This is the common thing that we see in the reinforcement learning literature. Okay, and this one shows the result. Okay, we can see that the greedy has the lowest cumulative reward, which is represented by the light pink color here. And we see that the greedy algorithm will have the highest cumulative regret. And for the epsilon greedy, we can see that for the cumulative reward, it has higher. Higher for cumulative rewards means better. And for the cumulative regret, lower means better. So epsilon greedy is better than greedy in both cumulative rewards and the cumulative regress. And then the Thompson sampling has the highest cumulative rewards, which is represented by green color, and lowest cumulative regress. Okay, so the highlight of this work, of this paper, is that we modify two changes to the simple setting. So we talked about the simple setting before, and we introduced two changes. First, the agent can choose multiple borrowers out of available borrowers, and we set it to 10, okay, 10 out of 100. And second, the set of borrowers is renewed in every time step. So we modify two changes to reflect the reality of the credit scoring, okay? And the question becomes instead, which algorithm perform the best? Because on the one hand, because we have in the simple setting that the epsilon greedy performs better than the greedy, and Thompson sampling performs better than epsilon greedy. But let's say by introducing these two changes, we allow the greedy algorithm to perform better than the simple setting because let's say that the greedy algorithm the agent has a lot of borrowers, a lot of information in hand, and then the algorithm will not be stuck to an inferior action. So we expect to perform better than before, but comparatively, we do not know yet whether it performs better than other algorithms in the same setting. And this is the result. So we can see that the Thompson sampling algorithm outperforms the epsilon greedy because of an efficient exploration. We can see that the green line for the cumulative rewards is higher than the purple line, okay? And for the cumulative regress, we can see that the dark purple line goes linearly. The cumulative regress goes linearly because of the uniform exploration. But because of the efficient exploration, we can see that the Thompson sampling has quite a lot lower cumulative regress here. However, by extending from simple setting to credit scoring, we can see that the greedy algorithm performs better than the Thompson sampling because let's say the pink line goes, let's say, beyond the green line and goes below the green line for the cumulative regression. With this in mind, we ask the question, how about, because before we used the two-dimensional setting. So now, how about if we increase the dimension to 20? What will happen? So this is the technical detail again, okay? So we need to make different things comparable. We multiply by adjustment coefficient. But the conclusion is that in the credit scoring setting with two dimensions, the greedy algorithm performs, let's say, significantly better than the Thompson sampling. But now if we increase the dimension, we can see that Thompson sampling now performs slightly better than the greedy algorithm. So the outcome changes. And this would imply that the efficient exploration is still beneficial, because before we have two-dimensional setting, which is maybe quite easy for the greedy algorithm to exploit. But now, by increasing the number of dimensions, the setting becomes much more difficult. And this is the result. We can see that the green line outperforms the pink line, which is the greedy algorithm, by a little bit here. Okay, it's a little bit hard to see here, but we can see that the green line goes a little bit below the pink line. So the recap, the result from the simple setting supports the common belief. Okay, because we can see that the algorithm with exploration, which is the epsilon greedy, outperforms the greedy. And Thompson sampling, which is the efficient exploration, outperforms the epsilon greedy. However, as the setting is extended to the credit scoring, because we introduce two changes, the Thompson sampling still outperforms the epsilon greedy. However, the greedy algorithm does not commit too early to an inferior action, and this results in the better performance than Thompson sampling. And let's say in further extensions, when we increase the dimension, we can see that the efficient exploration by Thompson sampling is still beneficial to the algorithmic performance, because when the ball characteristics are captured by a large number of features, Thompson sampling performs slightly better than the greedy. But let's say Thompson sampling outperforms the epsilon greedy, similar to the traditional results, okay, from the traditional reinforcement learning. And this is the end of the presentation, and we shall welcome from Q&A from the floor. Thank you.